Hello everybody. Welcome to this paper presentation. Today I'm going to present our paper, Parameter Efficient Fine-Tuning for Large Language Model Based Arabic to English Machine Translation, which was authored by me, Mujar Amina. I hold a master's degree in software engineering and distributed systems from the University of Jilali Bunama, and co-authored with Dr. Behlul Belhassan and Dr. Alian Hasina. I'm going to start with a brief introduction, and then I'll move to LoRa-based PEFT techniques, and PEFT is short for Parameter Efficient Fine-Tuning, and then I will move to methodology, experiments and results, and finally a conclusion. As we see in the recent years, the emerging large language models are increasing in size. As we see here, for example, Palm model has 540 billion parameters, which is huge. And these models, the backbone behind them is the transformer architecture. As we see here, it is composed of an encoder and a decoder. Now, the problem with these models is that it is very resources consuming to fine-tune them to downstream tasks, such as translation, as we see here. So the problem is, how can we efficiently adapt these models to Arabic to English machine translation? Our goal is to apply a set of LoRa-based PEFT techniques on existing large language models and evaluate the trade-off between computational efficiency and translation quality. I will start by presenting the first technique, which is LoRa, and it's short for low-rank adaptation, where in full fine-tuning, in regular full fine-tuning, as we see here, all models are updated, including attention and feed-forward layers, and they are, of course, updated based on the task. While in LoRa, the core model parameters are frozen, and LoRa introduces learnable low-rank matrices to the key attention component, updating them during the training, during training, while keeping the rest of the model unchanged. The second technique is DORA, which is short for weight decomposed low-rank adaptation, where the original model parameters are frozen, of course. The same thing happens with LoRa, and the weight matrices are decomposed here into magnitude, vector, and directional matrix for efficient fine-tuning. The process of DORA is that the weight matrices are split into two parts, the magnitude and the direction. The directional matrices are updated via LoRa's low-rank adaptation, as we see here, and the magnitude vector is fine-tuned directly after training. The magnitude and direction components at the end are combined. The third methods are actually similar. It's just that in LoRa we add the quantization, and in DORA we add the quantization. And after quantization, the core pre-trained weights of the model are frozen, ensuring that the base model remains intact during the fine-tuning process. Our methodology is as following. The model, we selected the RRT5 V2 base and the NLLB 200. 200 here is for the languages covered by this model. For the dataset, we used the parallel corpus, the UN or the United Nations parallel corpus with RRT5 and the Opus 100 corpus with NLLB. For tokenizer, we used the sentence piece and prefixing with RRT5 and Arabic English byte pair encoding with NLLB. For the fine-tuning techniques, we used full fine-tuning techniques for both, and LoRa and Dora also for both. And in RRT5 we used QDora, and in NLLB we used QLoRa. And finally we assessed the models. In full fine-tuning or in fine-tuning in general, or in this model, the objective was, of course, fine-tuning it for Arabic to English using the United Nations parallel corpus. As we see in this table, in full fine-tuning, all the parameters were updated. In LoRa, we updated the attention layers, the query key and value, and the output layer. In Dora, we used the same layers, but of course we used the magnitude and direction composition. In QDora, we added the quantization. The hyperparameters used were the learning rate, and the batch size was 2 due to memory limitations, and epochs were 5 to balance learning and prevent overfitting. And finally we used Sacré Bleu and Rouge metrics after each epoch. In NLLB, on the other hand, we fine-tuned it we used exactly the one with the 600 million parameter. For this multilingual translation. In this table, we see the full fine-tuning, where we updated all parameters of this model. In LoRa, we updated only the key and value attention layers. In Dora, we updated these layers, but before we composed them into magnitude and direction. In QLoRa, we added quantization to the LoRa composition, to the LoRa fine-tuning. The key hyperparameters, as we see here, the learning rate, which is 2 by 10 to the power of -5, to carefully adjust this large model. The batch size was 1 due to memory constraints, of course. The epochs were 3 for sufficient learning. And of course we used the same evaluation metrics as the previous one. Here we see the trainable parameters, LoRa, Dora, and QDora. They updated about 0.30% of the trainable parameters, and in RRT5, and in NLLB model about 0.20% of the parameters were updated. As we see here, full fine-tuning uses so much power in the GPU compared to the other techniques in both of the models. This is the RRT5 graph and this is the NLLB graph. and the memory allocated in full fine-tuning, we find that it was the method that allocated a lot of memory compared to the other techniques, and same with temperature, as we see here in both models, and in GPU utilization in general. The full fine-tuning used the most amount of GPU compared to the other models, as we see here, and the system CPU usage was also high in full fine-tuning compared to the others, especially here in this model. As for the evaluation metrics results, we see that LoRa, Dora, and QLoRa have very close results, but they're not very far from the full fine-tuning. And same with perplexity. At the end, I added the perplexity after the fine-tuning of the models. And in both models, we see almost the same results. Especially in this model, these fine-tuning techniques were not achieved closer results to the full fine-tuning. And if you notice, we have better results with this model more than A2I'25. And as a conclusion, we concluded that while full fine-tuning delivers the best result, as we see in the evaluation metrics, methods like LoRa, Dora, and QLoRa offer more efficient alternatives by updating fewer parameters using quantization, and they reduce memory and computational costs. In the future, we will focus on enhancing the translation quality instead. We won't focus much on the computational costs of these, of course, using these techniques. And we will also try to use bigger models, such as this model, an LLM-200 with 1.3 billion parameter. And thank you.